Right? Yeah, Fatiha. Thanks, Fatiha, for reminding me. Okay, so everyone's scared now? Okay, don't be scared. We still have time. Okay, so we talked about statistical inference for our module 10, part 2 of sampling theory. We talked about estimation, and we did not tackle hypothesis testing yet. We talked about what was a bias estimator and stuff like that. Okay, so this was what we talked about last time. And we also discussed which one should be chosen, a small variance or a bigger variance, which one is biased, which one is not biased. And then we also talked about confidence interval. And we can actually specify 95%, 99%, 92%. Actually, we can specify 66%. It doesn't really matter. It's just a value. We decide on what confidence that we want. But if we can decide, why don't we just decide 99%? Okay, so that's my question for today. And then we have 1 minus alpha is the confidence coefficient, and times it with 100, we get our confidence level, which is in percentage. And then what else did we talk about? I'm just going through the slides in a bit. And then we have these values that represent the percentage of the confidence interval. Okay, this module is already on Putra Blast, by the way. So 1.96 is our common one, which is the 95% that we love so much, or rather the textbook loves so much. Okay, so my question today is, where is it? Okay, it's here. Let me start. I'm recording, right? Yes. Okay. Why choose 95% confidence interval? I'm going to short form this as CI when we can choose 99% confidence interval. Okay, so remember that I told you, I don't think you remember though, but I'm gonna try to ask anyway. So remember that I talked about confidence interval between 95 and 99%. And I told you if we were talking about 95% confidence interval, it would be this much. And versus 99%, it will cover a lot more of the distribution. So over here, we can already see that one has a shorter width versus 99% has a bigger width as in like the gap, right? So with that in mind, is it okay for us to have a really, really big width when we are specifying the CI? Remember, if we are specifying a CI for a point estimate of a point estimate of mu, which is the population mean, we have a range that we have to specify for the confidence interval. Let's say, let me just write it down here. We're talking about a 95% confidence interval, for example. So this is going to be 1.96. The standard deviation of the population over the mean. If we don't have the standard deviation of the population, we can replace this by S. And then this would be sample mean minus with 1.96 standard deviation over square root of n. Okay, so that is bad handwriting. Let me try again. Okay, so this is what we know. And when we substitute these values that we know, the standard deviation, also the sample size, we can have a range. And this range we specify, for example, is going to be 10.96 to maybe 12.48. This is like random, okay? It's not from anywhere. So this is my CI of 95%. So I have a range, okay? So if this is 95, this would be my range. If I specify that I want a CI of 99, this value would change, right? Because the width is going to be greater. And we saw that for 99, where was it? For 99, okay, I can see 2.58. 2.58. Okay, so let's go back to our recap. So now it's 2.58 over here, sample mean minus 2.58, standard deviation square root of n, mu our point estimate that we're trying to find, plus with 2.58 standard deviation n. So my point here is, when you have to change your confidence interval, you are changing this value, right? And when you have a bigger confidence interval, this value also becomes bigger. Therefore, your range also becomes wider. And this is reflected in your graph. So the higher the desired degree of confidence, the wider the resulting interval will be. So I hope everyone understood what I was trying to say. An appealing strategy is to, the confidence level or reliability of the interval is inversely related to its precision. So the wider your confidence interval is, the less you know which one is the right value, less precise, right? When you look at this, these have like more values that you have to consider compared to this guy. So this guy is more precise compared to 99%. It is shorter in width and more precise compared to 99% because there's like less values to consider. So you know, like, oh, maybe we're talking about 10 values from here versus 20, for example. So I have less numbers to consider in 95% confidence interval. But you know that it's not going to be 10 because this is continuous. So it's like a range of values with no gaps. Okay, so an appealing strategy is to specify both the desired confidence level, if you want 99, if you want 98, if you want 95, and the interval width. So you specify the width that you are okay with, that your company is okay with, and then determine the necessary sample size. So we can actually change the sample size. So let's see this equation. Similarly, the width of 99% interval is width W equals to 2 times 2.58 standard deviation of the over the square root of n. So either you have this 2 here because, of course, you are talking about both sides, right? You're talking about this side and you're talking about this side. And these two, when you add them together, it becomes the width. Okay. When you add these two together, they become the width. So that is why you have 2 over here. Okay, let me just undo this. So that width is 2 times 2.58 standard deviation over the square root of n, or you can just say, you can just use this, where is it? You can just use, okay, it's not here yet. Okay, so I wanted to talk about the sample size. So if you were to increase the sample size, what you're doing is you are decreasing width. When you increase the sample size, you are decreasing width, but your CI remains the same. So this is one way of doing it. You want a certain CI, for example, you want 99, but 99 is going to be too big. You don't want it to be too big. You want a specified width that you already have in mind. So for example, you want your width to become 0.5. So you can put 0.5 here and you can calculate for what n that would give you a width of 0.5. So if my width is 0.5, this side would be 0.25, this side would be 0.25. Okay, so any questions about this one? Everyone's okay?
Okay, Doctor.
Okay, so continuing. So now we're going to continue talking about the sample size that we need for a confidence interval of specified width. So using the sample example given earlier, which was the average zinc concentration, I'm going to bring you back to the example that we talked about last week, the zinc. It was this one. The average zinc concentration recovered from a sample zinc measurement in 36 different locations. This was our N. 36 was found to be 2.6. This was our sample mean. Hence, the 95% confidence interval we found out, which was 2.5 to 2.7. This is our CI of 95%. Okay. You don't have to remember this question. You just have to know this value. I'm going to talk about this value in a bit. So the N was 36, and this was the sample mean. Okay, this is 95% CI. Okay. Whoops. Okay. So hopefully I remember what the values are. 2.5 and 2.7. 2.6 is the sample mean. Okay. Where is it? Where is it? Okay, it's here. Okay, so using the sample example given earlier, our sample mean was 2.6 and 95%. CI was between 2.5 to 2.7. This was our range or the interval. The interval that we calculated specifies the mean to be within plus minus 1. So our mean was 2.6, right? Plus minus 1, which was 2.7 and 2.5. It's the same thing. Okay, so assume that this interval is too wide to be useful. Assume that it is desirable to produce a 95% confidence interval that specifies the mean width to become 0 plus minus 0.05. So this is like super small compared to plus minus 1. Sometimes there is requirements that we need to fulfill, right? To do this, the sample size must be increased, but to what size? We already know the equation, so it should be straightforward at this point. Okay, so let x1 up to xn be a large sample size with n greater than 30 random sample from a population with mean mu and standard deviation so that your sample mean is approximately normal distribution. Okay, so this is your normal distribution. Then a level 100% times the confidence interval coefficient for mu is sample mean plus minus the z-score alpha over 2 times with your sample mean standard deviation, or this one, or this one. If you don't have the population standard deviation, you can just use the sample standard deviation. So the sample size necessary for a confidence interval to have a width W is given by this equation. I think the previous equation was much easier to look at. So we're talking about 95% confidence interval, right? So 2 times 1.96 because it's 95% CI. And then our standard deviation or our S, was it given? I don't remember. And then our width that they specified for us was 0.05. 0.05. Let me go back to the question again. Plus minus 0.05. So our width is actually 2 times 0.05. Aha, I just made that mistake on purpose. So again, if you see that plus minus, it means that it's double the size. Plus minus, right? Plus minus 0.05 on one side, 0.05 on the other side. So it's 2 times 0.05. So that becomes 0.1. 0.1, 0.05, 0.1. Okay, and then our S, so remember, let's see the question. What was the S? The population standard deviation is 0.3. So it's 0.3. It's not the S, it's the population standard deviation. So this is going to be 0.3 squared. So this will be your sample size that you need, whatever that is. So let's try to calculate that. I don't have my calculator. So 0.3. 0.3 divided by 0.1. Oh, it's this whole thing that is squared. Times 1.96. times with 0.3 divided by 0.1. Hopefully my math is correct. Squared. So I would get 138.29. Sample. So what does that mean? Oh, I already have it here. So this is actually wrong. When did I do this? So it's 1 point, sorry. The answer that we got here was 138.29, right? It specifies that it needs to be bigger than 138. So basically you have to round this off. I wouldn't say round off. Round off is not the right word. Make it a whole number. Let's just say that 139. Okay. So if it's greater than 138, you make it a whole number to become 139. So if it's 137.9, then it becomes 138. You get the idea. It's not round off because it's not yet 0.5. Okay, so I'm going to delete this because I don't remember when I did this one and it looks wrong. Okay, so you can attempt this on your own if you like. So the answer is 139. Size 139 will provide an estimate from the sample mean different from the mu by an amount less than 0.05. So what this means is when we got the sample size of 139, we are actually specifying that our point estimate mu is plus minus basically our question just now. So does anyone have any questions? I see I'm hearing some sounds. Oh. Okay, so this was what the question specified to us. And we found out what was the n, which was 139 using this equation. You don't have to memorize this equation. You just have to know this guy, the central limit theorem equation. Sorry, the confidence interval equation, and basically just have to find n from this equation. N is over here. Just substitute in here. You would get it. Okay, so there's no memorization involved. Oh, so that reminds me, for your final exam, okay, everyone, for your final exam, I won't be giving you equations, but I will be letting everyone to bring an A4 size paper. A4 size paper. You have two sides to your A4 paper, right? Use only one side to write all your equations that you want, anything. It's anything that you put on the A4 paper, as long as it is only one side, I will allow it. Because I'm not going to write down the equations. I'm not going to give you guys the equations in the exam. Only the tables, only the cumulative distribution tables, Poisson, binomial, stuff like that, but not the equations. Is that okay with everyone? So you don't want the... Okay, so everyone's not happy about this? I thought everyone's going to be happy.
Happy, Dr. P.
Okay, but just one side. You can write it as small as you like. You can type it out, I don't care, as long as it's only one side. So I will be checking your, we're going to call this cheat sheet. Cheat sheet, okay? It's not actually cheating, but you know what it means. Basically, it's like a handicap for you to help you in your, not handicap, I would say, I don't know the right term, but you get the idea. So I used this in my uni days. My professor also gave us this advantage because engineers basically don't remember anything. So cheat sheet is the way to go. Okay, so 0 point. Does anyone? Welcome. Does anyone have any question about this one? I'm gonna write this as part of the instruction for your exam as well, so don't worry. So any questions about the sample size for a specified with for a confidence interval? So everyone's okay with this? Gonna move on. Okay. So the solution is here. You can go back to the lecture video if you don't get it. Or you can also ask me through WhatsApp. Okay, so we also talked about one-sided confidence interval, if I'm not mistaken. We did. So basically the numbers are a bit different. For example, 95% for your two-sided confidence interval was 1.96. For one-sided, it's slightly different. And you should know how to find the confidence interval value or the z-score using the table. And we have also talked about this one. We also talked about this one. We also talked about the confidence interval for the difference between two means, which was just, the equation is just slightly different. You just have to know the equation. Let x1 up to xm be large random sample size of n from a population with mean of mu x and standard deviation of standard deviation x. Let also y up to yn be a large random sample size of n. So basically you have two populations. One is x, one is y. If the two samples are independent of each other because they are from different population, then a level 100% times the confidence coefficient. Confidence interval for mu x minus mu y is this equation. So this is your sample mean for x, sample mean for y. This is the z-score alpha over 2. And this is your standard deviation x, the variance from your population squared over the sample size of x. So basically your sample size can be different from these two populations. For example, your x is 50, but your y is 30 samples, because we're talking about central limit theorem here. So it has to be greater than 30. So 31 maybe. So 50 and 31. So a situation like that can happen, and a possible question in the exam as well. Okay, and you have to remember that if you don't have the population standard deviation or the variance, you can substitute with your sample standard deviation. This only applies for central limit theorem. Do not apply this to anywhere else. And there's something else I forgot. Okay, I'll let you know if I remember. Okay, so have we talked about this one? I think we already did this example because we already talked about the difference between two means. So now I'm going to talk about the last subtopic of the confidence interval, I think. Wait, proportions. Is there anything else? Oh no, we haven't talked about variance. Okay, two more subtopic for confidence interval before we start with our hypothesis testing. Okay, so confidence interval for proportions. So a sample of 144 microjoules is tested, and 120 or 83.3% of this meets the specification. So out of the 144 that we test, 120 meets the specification. I don't know what specification they are looking for, but 120 fulfills that. Let P represent the proportion or the probability of microjoules in the population that will meet the specification. We wish to find a 95% confidence interval for our P. So P is the proportion in the population. This is our sample. This is N. And 120 or the 83.3% is our probability. This is our P. So the estimate for, X is 120. Let me write that. N is 144. So these are two different numbers, and typically people will mix this up. So your sample size is always going to be N. The one that fulfills is X. Remember random variables? Random variables specifies success or fail. Success is your X. Or that could also be applied for binomial. Okay, so your X is the successful ones. So the estimate for P, or the probability, is given by P hat. We call this as P hat equals to X over N. So 120 over 144, you get your percentage over here, or 0.833. The uncertainty, or the standard deviation for P hat, is given by P times 1 minus P over N. So your P is, did it specify here? Since the sample size is large, it follows the central limit theorem. Therefore, because our sample size is 144, right? Therefore, the point estimate of the population proportion P with a 95% confidence interval follows the inequality below. So P is less than P hat plus 1.96 times with this guy, because this guy is our standard deviation for the P hat. Now, instead of your sample mean, instead of this, we are changing this to P hat and changing this to standard deviation of P hat. It's just changing the elements of the inequality. So instead of mu, we're talking about P. Instead of X, instead of sample mean X, we're talking about P hat. So P hat is like the sample mean. The P is like the population mean, or the point estimate of the population. Okay. So let me write that somewhere. Mu. And this is just a Z alpha over 2 score. Okay, so two-sided confidence interval for proportion. When we have two-sided, you know what's coming next. It's one-sided. It turns out that replacing the population proportion P with the sample proportion P hat tends to make the confidence interval too short. So what they're saying is, using this P hat makes the interval too short and not accurate. This effect can be largely compensated by modifying both N and P slightly, of course. So let X be the number of success in an independent Bernoulli trial with success probability P, so that your X, random variable X, follows a binomial distribution with N and parameter N and also parameter P. So define your N as equals to, what do I call this? And let's just call this N hat equals to N plus 4, and can't call this P hat. Let's just call this modified N, because I don't know what this is called. Modified. We're changing this N to become better suited for our estimation. So we have to modify our N to become N plus 4. And then this is our P modified, which is 120 that we talked about earlier, 120 plus 2, which is 122, divided by this one. This is 144 plus 4. So it's 148. Then a level 100% times the confidence coefficient interval for P is this guy. So modified P plus minus Z alpha over 2, and P modified times with 1 minus P modified over N modified. You have to square the whole thing. If the lower limit is less than 0, replace it with a 0. If the upper limit is greater than 1, you replace it with 1. So since we're talking about probability is always between 1 and 0, right? This is different, entirely different than your sample mean. Your sample mean is basically like anything goes, like 12.4, 100, can be anything, right? But for probability, we know that it has to be between 0 to 1, because the maximum number that a probability can have is 100% or 1, and the minimum is the 0. So if, let's say, your estimation of the confidence interval gives you a range as such, 0.1 to 0.9. So 0.9 is good. You're good to go with the 0.9. But this is obviously not within the range. So you have to change this to become 0 0.9. So this will become your confidence interval for the proportion. Okay, so this is what it means when you have to replace your limit, your lower limit, with 0 if it is negative. Okay, so let's try to do some example regarding this because it looks a little bit confusing. So this is for one-sided confidence interval. Of course, it's just the same concept as your sample mean. Previously, we were talking about two-sided, so your z score was alpha over 2. But for one-sided, your z is just alpha. Remember, when we're talking about two-sided, we have to divide the confidence. We have to divide it by 2 basically. Alpha over 2, alpha over 2, minus, plus. Whereas when we're talking about one-sided, we're just talking about alpha. So this is why our z is different. So your modified p minus with the z alpha times with this term. And the level 100%. So basically it goes from p plus and p minus z alpha, this term. If the lower bound is less than 0, replace it with a 0. If the upper bound is greater than 1, replace it by 1. It goes for both two-sided and also one-sided confidence interval for proportions. Okay, so let's do an example. Interpolation. Oh, I should give you a break. Let's do this example and take our break. So interpolation methods are used to estimate heights above sea level for locations where direct measurements are unavailable. So basically, they're just giving you an intro about this problem. A weighted average method of interpolation for estimating heights from GPS measurements is evaluated. These are all engineering stuff. The method made large errors. This method that we're using made errors at 26 of the 74 sample test locations. So 74 is your sample test location. We already know that this is going to be n. And then the method made large errors of 26 out of the 74. So this is going to be your x. If we are assuming the x is the success, or like the main question. Find a 90% confidence interval. The CI is going to be 90% for the proportion of locations at which this method will make large errors. So yes, indeed, we are talking about the locations that the method made large errors, which was 26. 26 out of the 74. So 1 minus alpha, this is 1 minus alpha times 100%. It's going to be 90%. So solve for your alpha. I don't remember what the value for alpha is. So let's see the solution. The number of successes is x equals to 26. Number of trials n is 74. Therefore, we find out what is the modified n. So this was your first step, specifying what is your x, what is your n. Second step is to find out your modified n and also your modified p. Modified n is obviously n plus with 4. Your 4 is a constant. You don't change this. You don't make it into n plus 3, n plus 2. No, it's always a 4, always. They already made a bunch of experiments with this and it works. The estimation works. And then your modified p is basically x plus 2 divided by your n modified, which is this guy. Okay, so this is your value for your modified p, 0.3590. So first step, x and n. Second step, modify your x and n. Sorry, your x and p. Sorry, your n and p. Oh my God. And then you find out what is the term, the standard deviation for your modified p, which is the modified p times with 1 minus modified p divided by 78, which is your modified n. So this is your value. Therefore, you know that for a confidence of 90, the alpha over 2 is 0.05. Actually, I don't, because I don't remember. So your z alpha is 1.645. So this is your range that you will get. So your p, if we're going to write this like this in the form of an inequality, it would be 1.645, because this is your Z alpha over 2 plus with your this term, this guy over here, your standard deviation of the P modified, 0.0543. This guy is your Z alpha over 2. Where's your P hat? Wait. I forgot a term. Let me rewrite this. P, your P modified plus with Z alpha over 2 and this guy. Okay, so this would be 0.3590 plus with Z alpha over 2, which is 1.645, and your term, this modified standard, this standard deviation for your P modified, which is 0.0543. Okay, same case over here. P modified minus this term. P modified is 0.3590 minus 1.645, 0.0543. You don't have enough space. Let me just write it in the general form. Minus Z alpha 2 and this guy. Okay, so your P, this is your P. Wait, where is it? No. This is your P modified. Where is it? It's here. This is your P modified. Your Z alpha score is here. Okay, and then this is your standard deviation for the modified P. Okay, so basically just using the equation correctly, knowing what your X is, knowing what your N is, modifying your N and P. Okay. And then we're going to move on. No, wait, we have to take our break first. Let's come back at 10:05. I know everyone is dying right now. So take your break, come back at 10:05. If you have any questions, you can ask me. Same project. Sharing is paused. Sampling theory. Is it time? Okay, so it's already 10:05. Okay, I want everyone to go to Putra Blast and look at the assignment. I'm going to share the Putra Blast for a bit. So for chapter, where is it? It's not it. So you can just look at my screen. Later on, you can access the Putra Blast. Putra Blast. So I'm teaching 2 courses. Your stats is 3004. You can see my screen, right? Guys? Can you see my Putra Blast?
Yes.
And there.
Okay, so we already talked about, we already did assignment week 2 and assignment week 9. So if you did not manage to submit assignment week 9, please do submit it, even though you're late. And then we have a new assignment week 12. So you have 7 days and 13 hours to complete this. So this is what we're dealing with. Share screen. So assignment, this is assignment for module 10. So for module 10 part 1, there is your central limit theorem. I did not include your estimator versus estimation exercises, which means that there's not going to be a calculation related to your estimator topic, but definition is still fair game. Definition, or like your general understanding of the estimator estimation, can still come out in the exam, but not calculation for your estimator estimation subtopic. Your central limit theorem, yes, very, very popular topic. And then for module 10 part 2, you have your large sample confidence interval for population mean. We already talked about that. And then for proportions, we are talking about that right now. And then for the difference between 2 means, we already covered that one as well. And then for variance and standard deviation, we're going to talk about it right now. And that is it. Not too much. If you have your discussion, it's going to be bearable. So 7 days, try your best, because module number 7 assignment is coming up soon as well. Okay, I know it's a lot of work, but it's to help you boost your grade, because your test 1 is, okay, so let's continue. So now we're going to talk about the confidence interval for variance and your standard deviation. This is the last part for module number 10. Hooray. So let x1 up to xn be a random sample from a normal population with variance given. The sample variance is s squared, and this is the equation. The quantity, so this is your equation, and they rearrange this equation. Okay, let me try to show this to you guys. So you have something like this, minus the sample mean divided by n minus 1. So what they did was, they moved this to the other side. So they moved this. So now it becomes n minus 1 times with s squared equals to the summation of the x minus with the sample mean. Sorry, I missed out the square. And then they're not done yet. Since they wanted to divide this guy with a variance, so if you are dividing the variance in one side, you also have to do it on the other side, because balancing. So now you have something that what they call as the chi-square distribution, Basically, they flipped around things, added the variance, and they said, oh, this looks like a chi-square distribution. Let's use it. So why not? So it has a chi-square distribution with n-1 degrees of freedom, and your chi-square distribution is given by this weird-looking x squared. Weird-looking x squared. I don't know what to call it. I have to figure out what it's actually called. So this is, let's just call it weird-looking x squared n-1. So your x squared, this is like, doesn't change ever. The square does not change. But this guy, n-1, the degrees of freedom, yes, it does change depending on the question. So let's look at that. So when we have a distribution, a new distribution, obviously we will have a table called the chi-square distribution table, just like our cumulative, just like our binomial, just like our Poisson. So we have to learn how to use the table. Okay, so what is the chi-square distribution? I'm still recording, right? Yes. So this chi-square distribution has two important points. The first one, it is not symmetric. So your normal distribution is very symmetrical, not very, it is symmetrical with your mean in the center, right? And it was very easy to use the normal distribution because it's very symmetrical and it gives us a lot of information. However, the chi-square distribution is not symmetric, so we cannot approach it like we would a normal distribution. They are skewed to the right, which means that they are like slightly flattened towards the right. They are skewed to the right. So they are, you know, tapered down towards the right. So the values of the chi-squared statistic are always greater than or equal to 0. So remember, when we were talking about normal distribution, I said the normal distribution, or the textbook said the normal distribution always has an area of 1. But for chi-square distribution, it can be equal to 0 or greater than 0. So it's not necessarily, wait, let me think about that statement. Okay, hold on to that. I need to confirm on that statement. They are never negative. Okay. So this is the chi-square distribution. This is a chi-square distribution with 5 degrees of freedom. And then you have your 10 degrees of freedom. Then you have your 20 degrees of freedom. This one is with 1 degree of freedom. So as you can see over here, the greater your degrees of freedom, the wider your distribution is. The wider your distribution is. So plots of chi-square probability density function for various degrees of freedom. The curves are skewed to the right and all the area under the curve is over the positive part of the x-axis. So you will not have a chi distribution over here. You will not have a chi distribution down here or down here. It will always be the positive side of your x-axis. Okay, so that is the characteristic of the chi-square distribution, which is also a potential question. Because the chi-square distribution are not symmetric, confidence interval for variance have a different form than those for means and proportions. Of course, this is why we are looking at this. Okay, so remember that our normal distribution, when we were talking about the z-square, we said for two-sided, we can easily say, okay, this is z alpha over 2, this is z alpha over 2. The addition of these two guys will give me alpha. But for this one, you have to distribute the alpha over 2 on both sides, but they will not have the same, they will not have the same z, they will not have the same z. Okay, so let's talk about that. Probability density function for the chi-square distribution with k degrees of freedom. So they did not specify, so k is your unknown. The values chi-square distribution with k degrees of freedom, 1 minus alpha over 2, and your chi-square distribution with k degrees of freedom, alpha over 2. So this one is 1 minus alpha over 2, and this guy is alpha over 2. So instead of alpha over 2, we have alpha over 2 over here and 1 minus alpha over 2. Just bear with it. I know it looks confusing. Contain the middle 100 1 minus alpha percentage of the area under the curve. So we are specifying a confidence interval right here, even though it does not look symmetrical. So question, find the upper and lower 0.025 points of the chi-square distribution with 10 degrees of freedom. So this is how they would describe it. Chi-square distribution, down here is your K, or your degrees of freedom distribution. Okay, so chi distribution, 10 degrees of freedom, we are trying to find 0.025. Let's look at the table. So we are talking about the degrees of freedom being 10. And then we are specifying the upper and lower 0.025. Let's look back at the question. Find the upper and lower 0.025 points for the chi-square distribution with 10 degrees of freedom distribution. So use the row corresponding to 10 degrees of freedom to find the upper 0.025, look at under 0.025, and look at alpha 0.975. What does this mean? This is your alpha over 2, and this is your 1 minus alpha over 2. Or is it the other way around? Let's see. I need to look at the table. So 0.025, the upper and also the lower. So 0.975 is basically 1 minus 0.025. Okay. So let's see the table. One was 0.025, this value, and the other was 0.975, which is 3.247. So your 3.247 would be here, and your 20.483 would be, of course, the further side, 20.483. Okay, let's see. We have the answer here. Oh, no, we don't. So to find that the lower 0.025 is 3.247 and the value is, yeah. Let me just draw this again. So this would be 20.483 and this side would be 3.247. The upper end, this would have a value of 0.025 and this would have a value, no, sorry, 0.975. So 0.025. It's very, even I get confused with it. So this is the 0.025. And this is our 0.975. Little bit odd, right? Okay, I'm trying my best to make this skewed to the right. So hopefully that makes sense to you. So let's delete this so that you guys can look at this lecture note. Okay, so that was the first question. Let's do another example so that we can help ourselves to better understand this. What time is it? Okay, we have time. So a simple random sample of 15 pistons is selected from a large population whose diameters are known to be normally distributed. So here it says normally distributed. The sample standard deviation of the piston diameters, the sample standard deviation of the piston diameters is S equals to 2. Find the 95% confidence for the population variance. So what does it mean when they are saying a simple random sample of 15 has a normal distribution, and then they ask us to find the 95% confidence interval for the population variance? Can we still use the chi distribution? Can we use chi distribution or not? Anyone? Yes? It's okay if we get it wrong. Can we use it or not?
Not.
Because? Anyone wants to help your friend? Actually, I did not know who was talking just now. So your friend said you cannot use the chi distribution. Any answers? Why? So this could be a question in the exam. So you have a simple random sample, have a normal distribution. What do you assume about the sample? Sorry, the population is normally distributed. What do you infer about the sample? Does it follow a normal distribution or not? Let's try to break this down. So population is normal, okay? And then we want to know if our sample will also follow a normal distribution. The number is 15. Does that satisfy the central limit theorem or not? What was the N for central limit theorem?
30 or more than 30.
30 or more, right? So N must be greater than 30. And it says that the central limit theorem says that whenever you have a sample size that is greater than 30, it doesn't matter what your population distribution is. It can be Poisson, it can be uniform distribution, and you would still get a normal distribution. But here, our sample size is 15, but it is coming from a population that is normal. What would be my sample distribution be? Will it follow the central limit theorem? The answer is no, right? But what would be the distribution? Still normal. It follows the distribution of the population, guys. This was the question in the test too. I haven't marked yet. Now I'm scared to mark it. Okay, so remember, if your population is normal, your sample is normal, even though it does not satisfy the central limit theorem. If your population is not normal, for example, it follows a uniform geometric, forgot the name, uniform something distribution. Remember that we had like something like this. Okay, let's say it follows this guy. This is the population. We take a sample out of this population. It's not a normal distribution. It's something else. So the central limit theorem said, we don't care about that. As long as your N is greater than 30, you would get a normal distribution for your sample. So that was the beauty of your central limit theorem. Sample is normal if N is greater than 30. This is the beauty of central limit theorem. And this is how we approximate a lot of stuff in our daily life. If not in your daily life, then in a lot of manufacturing companies. Okay? So population normal, therefore your sample is also normal. If your population is not normal, you only have, the sample will only be normal if it follows central limit theorem. Okay, so now look back at the question. What is the sample distribution? It's supposed to be normal because the population is normal. Okay, is everyone okay with that? That question is going to be part of the final exam. You have to understand the central limit theorem. Is very, very important. I'm scared now. Don't make me scared. Okay, so the sample standard deviation of the piston diameters is S equal to find a 95% confidence interval. So they 95. For the population variance, that guy. So our N is 15, selected from a large population, which is normally distributed. The answer is yes, we can use our chi distribution because, let's go back to the definition. Let x up to xn be a random sample from a normal population. So even though we had to use chi-square, but the population had to come from, the sample had to come from a normal population. So this is your condition to use the chi-square distribution. It has to come from a normal population. Typically, variance and standard deviation is not a common question, but you still have to know how to use the chi-square distribution. Actually, I'm skipping t distribution because it's just too much. We have not covered hypothesis testing yet. So chi distribution we have to know. I'm skipping t distribution. If you see that in the textbook, it's not going to be in the exam. Okay, so let's go back to this example. That was tough. So there's a lot of explanation and I want to go through this one by one with you guys. So again, a simple random sample of 15 pistons is selected from a large population whose diameter are known to be normally distributed. This satisfies the condition for our chi-square distribution if we're going to use it to find the variance or the standard deviation. The sample standard deviation of the piston diameter is S. Find a 95% CI. So again, to construct a 95% CI, let me zoom into this one. Okay, so we know that if we were to rearrange everything, remember that we arranged the equation just now and they said, okay, this follows the chi-square distribution, so let's follow that. So this was it. So n minus 1 s squared divided by the variance. So your n is going to be 15. 15 minus 1 is 14 degrees of freedom. So this is your K. From the chi-square distribution, we find that the lower and upper 0.025 points of the chi-square distribution with 14 degrees freedom distribution are this guy. Now the question is, why are we looking at the lower and upper 0.025? Anyone? Why are we looking at lower and upper of 0.025? Let's try to make sense of things. If I give you the solution, you don't understand how to read it, there's no use, right? So why are we looking at the lower and upper 0.025? Anyone? Just try to guess. No one? So is this too hard? So our n is 15. K is our degrees of freedom, which is n minus 1. This is 14. We want a 95% confidence interval, which means that 1 minus alpha is 0.95. Therefore, alpha is 0.05. Therefore, alpha over 2, 0.025. Does that ring a bell? So this is where the 0.025 comes from. So your alpha over 2 is still like the main character of the chi-square distribution. We first find the confidence coefficient, find out what is our alpha over 2 because this is a two-sided thing, even though it's not symmetrical. So once you find out what is the alpha over 2, you try to find out what are the values for that. So let's look at our table. So 0.025 upper and lower should be the same as before. So 20.48 and 3.247. Sorry, the degrees of freedom is different, so it's not the same. So the degrees of freedom is 14, so it's over here. Uh-oh, I don't have the thing. 1, 2, 3, number 3, 1, 2, 3 over here. And then 1, 2, 3, 1, 2, 3 over here. So I'm looking at 14 degrees of freedom, and this corresponds to 0.975, and this corresponds to 0.025. So that would give me 26.119 on one side and 5.629 on the other side. So let's go back to the solution. So this is the values that we got from the table. So we're not done yet. So these are the values that follow the chi-square distribution. We can't say hooray yet, it's not done. put another way for 95% of the samples that might have been chosen. So basically what they did here is that they rearranged this so that they could solve for variance, because variance and standard deviation is what we're trying to find. So we have this inequality. We try to arrange it in a way that it tells us what is the range for our variance. In this way, we can't really say much. So we have to rearrange it. So what they did is they bring n-1 over here. If they are bringing it on one side, they have to bring it on the other side as well. We also brought the s down here. So let me try to write that down. So 1 over variance, 5.629. This is the value that we got from the table. So n-1 s squared. Again, if I'm putting it down here, I have to put it on the other side because balance. n-1 s squared. Okay, taking the reciprocals, which requires us to switch the order of inequality, we obtain a 95% confidence interval for our variance. So they said that if you want to switch this, to go up, you make it into your numerator. You want to switch this, basically, you have to change this sign as well. Very, very important step. So variance is going to be up here, 1. You're flipping it, right? You're flipping it. You have to bring this to the other side. 5.629. Sorry, I'm flipping it. This is like that. So now we are flipping it. You either flip the signs or you flip this the position of your inequality. So I want to flip this to the here and here to here. So I just maintain my signs over here. So let's flip this guy instead. You can do it both ways. Both are correct. Okay, so that would give me something like this. n-1 s squared, 5.629. And this side would be n-1 s squared, 26.119. Okay. And then in this example, our s squared is known, this guy. So we can substitute s squared for the value that is given. And our n is also known, it is 15. So we can just substitute and find out that our inequality or our variance is between here, this value. Okay. So a lot of steps. The most important step is to remember to flip this. Find the chi-square distribution, flip it, and then just substitute the values to get your final answer. So let me try to number this. Your first step is to find your alpha over 2, right? Your degrees of freedom and alpha over 2. Or maybe just number 1 is finding your degrees of freedom. Number 2 is finding your alpha over 2. And then finding the chi-square distribution, your upper and lower, right? And then for number 4, you switch. You try to rearrange your equation to solve for your variance. And then number 5 is just substituting and getting your final answer. A lot of steps, but with practice, I know you can do it. Okay, so any questions about this one? So did everyone understand the solution or not? Everyone's just lost now. You still have time. Don't sleep yet. Okay, so I'm assuming everyone understands this and will score perfectly in the exam. Moving on. Okay, we're done with confidence interval. So let me introduce you to hypothesis testing. But before that, any questions about confidence interval in general? Any concerns about the questions that will come out? Anything about module number 10? Nothing about module number 10? Okay, so here is a table of a bunch of stuff that we did not cover. We only covered like, I think like 1/4 of this. So basically we did not cover everything. I skipped a lot of stuff because as long as you understand one part, I believe you can just apply it later on if you need to. So this one is an example of what I did not teach you guys, the T distribution. The T distribution is used for small sample sizes that do not fit in the central limit theorem. But I'm not going to test on that. And then I also did not cover this guy. Also using T. So everything else we did cover, and anything that uses the T distribution is not going to be on the exam. So if you see it in your textbook that you're using, just leave it. You don't have to worry about it. But of course, you can try to learn on it, learn the T distribution on your own if you want. Okay, moving on to hypothesis testing. So hypothesis testing, okay, let me share first. Hypothesis, module 11. Okay, so for your group project, you will be exploring about confidence interval and also hypothesis testing. So hypothesis testing is basically asking a question and trying to prove whether your hypothesis is correct or not. So for today, I want everyone, no, I haven't given you guys your groups yet. So after I've given you guys your groups, you will form a hypothesis question. And as we learn our topic, you will try to collect data from your classmates. That's why it's only 10%. If it's going to be greater, I want you guys to survey the public, but I don't think we have the time. So collect data from the classmate. Basically, you will form a Google form using your hypothesis question, collect the data, and try to prove or reject your hypothesis. And on top of finding your hypothesis, you will also need to form a confidence interval. So these are two different things. So we're going to talk more on that. Collect data from classmates. So you have 59 classmates. You have 59. I have 59 students in my class. If one group has 5 students, your population is going to be 54. Population, not sample. So what is your population? The population is the students of ENG3004-6 under Dr. Nadia Hussaini. And then your sample population must be greater than 30. So from the 54 data that you collected from your classmate, you select randomly 30 data and you make your hypothesis later. We're going to learn how to do that. Okay, so hopefully everyone is excited for maths. Okay, so let's go with hypothesis testing. So let me introduce you guys to what it is in general. So let's say we have a sample mean. We have a sample mean that is 12.68, for example. And our standard deviation is 6.83. Okay, so the question that we're going to ask ourselves is mu greater than 11. What is mu? Mu is the population mean. Is mu greater than 11? So based on the sample, I can just say, yeah, the sample is 12.68. Therefore, your population mean should be greater than 11. Simple. But you have your uncertainty here. What does that uncertainty mean? Uncertainty means that your data is going to be spread out from the mean. So if your mean is here, it is spread out, which means that it could be anywhere within that standard deviation. So it could be greater than 11 or it could be less than 11. So if you have uncertainty or if you have a sample standard deviation, you know that you cannot be certain of this value. You cannot be certain. It's just an approximation. So this is why we have standard deviation, right? From the beginning of the class, it tells us how spread out the data is. It means how uncertain we are about the approximation. So our standard deviation is quite large. So what can we do with this data? How can we prove that this is true? So can we use CI? CI tells me how confident I am about something, right? So for example, I want to specify a 95% confidence interval for a point estimate mu based on my sample over here. I don't know what my mu is. I want to estimate based on the CI, right? And we have talked about CI in a way that we were point estimating this guy to be plus, what was it? Z alpha over 2 and this guy. Oh, this is minus. And from here, from this inequality, we could get a range. We could get a range of our CI. And let me give you the CI really quickly. For this example, it's going to be 10.79 mu 14.57 for a confidence interval of 95%. So this is my CI for a 95%. Does this CI tell me that mu is greater than 11? No, not really, right? It gives me the range, tells me how confident I should be with this range, but it doesn't tell me for sure that mu or the population mean is indeed greater than 11. So what is next? I tried the confidence interval. I could not prove it. So the next thing is to use hypothesis testing. Let me just call this HT. Okay, so in H, the question of mu greater than 11 is called hypothesis testing. This is the actual story. Hypothesis testing, this guy. This statement or the mathematical statement is hypothesis testing. We will test this statement. Okay, so to test the hypothesis, this slide. Duplicate this. So everyone is following me so far, or is this like super boring? I think everyone is sleeping. Are you guys sleeping?
Noted.
Okay. For some reason, I'm just gonna believe you guys. Okay, so hypothesis testing. Oops, sorry. I'm going to try to break it down here. So hypothesis testing deals with two types of hypothesis. Just now I gave you only one, right? So let's see how we can fit that into this. So one is called the null hypothesis. And we label this, or we denote this as H0. And the other one is called alternate hypothesis. And we label this as H1. So we always will try to test our null hypothesis. Our null hypothesis will always be on trial. We're not going to test H1. We're always going to be testing H0. And H0 will be on trial, just like Johnny Depp and Amber Heard. So these H0 is the one on trial. it is innocent until proven guilty. For in this case, in the mathematical sense, it is true until proven otherwise. So we will always assume that our null hypothesis is true until we find evidence that it is not. So how do we find out whether this guy is true or not? So I'm going to introduce you guys to another term. It's called the p-value. Don't worry, I'm just introducing terms. Later on, we're going to apply this in example. I don't have space. Let me try to group this. Okay. It is true until proven otherwise. And how do we determine whether or not it is true? We will estimate this using a value. Doesn't make sense to estimate something true or not using a value, but this is how it goes. So the p-value goes from 0 to 1. So the smaller the p-value is, the smaller the p-value, you reject H0. So why? We're going to talk more about that. So smaller p-value, reject. Oh wait, this is not a good flowchart. So small, so we have two values here, small and large. Small and large. Okay, so if my p-value is small, I'm going to accept my H1. If my p-value is large, I'm going to accept null hypothesis. I can rephrase that statement. If my p-value is small, I can reject the null hypothesis. If my p-value is large, I can accept my null hypothesis as possible. I don't have to talk about H1. I can just talk about H null hypothesis. Small, I'm going to reject this. Large, I'm going to accept this. Because basically our null hypothesis is on trial. Okay, so let's take a look on an example for that. So this is like all the wordings. You can read this if what I said was too fast. Okay, so here we have a scenario. A certain type of automobile engine emits a mean of 100 milligram per second of oxides of nitrogen at 300 kilometer per hour. Basically, it's like an F1 automobile. A modification to the engine design was proposed by the company that may reduce the emission of the nitrogen oxide. This modified design will be put into production if we can prove that the mean emission rate is less than 100. So this is what they are looking for. So we need to prove that the modified design will emit less than 100 milligram per second. This is what they want. If it is true, then they will put the new design for production. If not, they will just continue with the original production and lower down the cost. I mean, not bring more cost into the production lah. So a sample of 50 modified engines are built and tested to test this. So the sample for this 50 is 92 milligram per second. So this is the emission, the average emission of nitrogen oxide. And this is your standard deviation. Again, you have your standard deviation. It means that you cannot be certain that your sample is true. You cannot be certain that it is 100% correct. Sometimes there is a difference in the sampling. You have two different samples. One is 92, the other is 105. That could also happen. So your standard deviation tells you, okay, this is super unreliable. You need to test it further. So your uncertainty is quite large here, so it is unreliable. So if there was no uncertainty, then we can be certain and conclude that the modified engine emits less than 100 milligram, but we do have this. So the 92, which is less than 100 milligram, is just a sample. We don't know for sure if it's true or not. we need to know what is our mu. Oops. Okay, so since there are uncertainty in the sample mean, this would mean that the population mean mu is greater or lower than 92. So the sample is just a sample. We need to test it to see if it's true or not. Okay, how much time do I have left? So I have 10 more minutes. I'm going to continue this in next class. Okay, so tomorrow I'll come up with the instruction for group project and also your group team members. And hopefully we can learn more about hypothesis testing and how you can apply it for your project. Okay, so that's it for today. Take care, have a great lunch, have a great rest of the day. Don't forget your lunch. I'll see you tomorrow. Bye-bye, guys.
Thank you very much, Doctor.
Thank you,
Thank you,
Doctor.
Doctor.
Thank you, Doctor.
Bye.
Thank you, Doctor.
Okay, bye.
Thank you, Doctor.
You're welcome.
Doctor,
Yep.
hypothesis testing masuk final tak? Hypothesis testing
This is masuk.
masuk juga. Oh, okay. Okay, Doctor, thank you, Doctor.
Okay, bye. See you later.